Assalamualaikum and hi everyone, I'm Dr. Wan. In this video, I will talk about the introductory and fundamental part of Bionano. There will be three topics that will be covered, which is the definition part, the appreciation part, and the scale part. For each topic, we will discuss further on its subtopic. For example, under the definition part, we will discuss what is the biotechnology, the definition of biotechnology, the Bionano and nanobio. Further down the road, we will give an example to strengthen your knowledge. The example here can be elaboration, can be calculation, can be demonstration, etc. So be sure to check it out. So let's go for the first topic. Because this video is about Bionanotechnology, let us look at each of its parts, the bio part, the nano part, and the technology part. In general, bio deal with something living, nano deal with something small, and technology deal with something that related to application part. Here, the bio can be a living organism, for example, the bacteria, yeast, fungi, or the product of it. Bio here also related to the process. For example, you can produce a wine or a bread using a fermentation process by the yeast. It can also be a very building block for that living thing. For example, like cell, like a DNA, peptide, and so on. It also means a principle that governs a biological things to do their activities. For example, specificity, the complementary, the self-recognition. All of these can be put under the one umbrella called bio. On the other hand, the nano part deal with the dimension, the scale. Nanometer itself is defined as a billions of meter, but the range here is not set on stone. Sometimes something that is 200 or 300 nanometer also considered under the realm of nanometer. And the technology here deal with something related to techniques. The application, for example, of technique is the fabrication, the synthesis or manipulation of something to make something else. Before we define the term bionanotechnology itself, let's look a little bit further on nano. Because bio part and technology part, that is common sense. Everybody knows it. But nano, why nano? When all this started, it all started when Richard Feynman, a Nobel laureate, gave a very famous talk entitled "There Are Plenty of Room at the Bottom." In his talk, he envisioned entire book of Encyclopedia Britannica can be put on the tip of the needle. Now it's a reality. You can put more than the entire collection of Encyclopedia Britannica in one thumb drive. But on that time, remember, this talk is given in 1960s. To be able to envision that vision is quite something. Hence, this guy is considered as the father of nanotechnology. You can watch the talk on the YouTube. So now back to the definition. If we remove a nano from the equation, we got biotechnology. So what is biotechnology? So it has two components, the bio and technology. So just simply combine what we learned in the previous slide. The use of living organism, product of living organism, or biological process for the purpose of developing something using the techniques. Making bread, making wine, making cheese. All of these are biotechnology. Because you use a living thing, in this case, a yeast or fungus, to produce that stuff. Modern biotechnology typically deal with producing something that is more specific, more targeted. For example, penicillin production from fungi. A fungi, a living thing, can produce many things. So modern biotechnology, they try to pinpoint, try to isolate this penicillin out and try to produce this isolate in a larger quantity. If you put nano, if you add nano in the definition, you can get either bionanotechnology or nanobiotechnology. The priority always to those who come first. For example, for bionanotechnology, you use bio part. In this case, the biological building block like DNA or peptide or its principle to produce something at nano scale. Example of bionano is that you use DNA oligomers, short chain of DNA, peptide, which is the short chain of protein, or protein fibril as a template for metal nanowire or interconnect so that you can use it for molecular electronic. On the other hand, nanobiotechnology focus on nano part first. And this nano part doesn't necessarily mean you need to take it from the biological part. For example, here is a mini computer. Beneath this copper heat sink, you will find a integrated circuit or the brain for this computer. within that brain of computer, there are billions of transistors. The silicon industry doesn't use any biological stuff. They just physically making it smaller using a technique called lithography. Example of nanobio is that you use a fabrication or manipulation at nanoscale in order to produce more sensitive and more accurate diagnostic tool. You can also use a nanometric in order to encapsulate a drug for controlled drug release. And this nanometric can be made of, for example, like from the cellulose, nanocellulose. You can also use nanometric that is fabricated using nanotechnique, like electrospinning for tissue engineering purpose. You can also create a nanorobot for surgeries. You can also create a nanomachine as an alternative for functional organ in your bodies. So all these you use nano stuff in order to help the bio stuff. To make this difference simple, let's say I have a wire. I can make this wire from DNA. So that is Bionano. Or I can make this wire smaller by cutting it, and then use that as an electrode for the medical device, and that is nanobio. However, the distinction between Bionano or nanobio is quite arbitrary out there. For example, here on the left you can see a book called A Plenty of Room for Biology at the bottom, an introduction to Bionanotechnology. But if you see the image itself, it's a robot, and this robot, which is not really seem to be made from the DNA or peptide or any biological stuff, injecting something on the blood cell. So by definition, this is the case of nanobiotechnology. If you look on the right, it's a highly cited paper from a Nature Biotechnology. The title itself is Fabrication of Novel Biomaterial Through Molecular Assembly. This paper talk about using a molecular thing like DNA peptide to produce something. It's much more geared to Bionanotechnology. However, if you look at the title here, it is Nanobiotechnology. So we can say that Bionano and Nanobio is cross-pollinated across each other. Hence, in this video and onward, we are not specifically focused on Bionano, but mostly focused on Bionano, but we also deal with the Nanobio. In general, manufacturing can be either bottom up or top down. Bottom up is like you build your house, you build brick by brick. Top down approach is like from the tree you get the paper. It's basically stripping down the tree, the cellulose, getting the pulp and make a paper. So in our discussion, Bionano, because we built something from the small stuff like the DNA, like peptide and so on to build something else. So it's considered as bottom-up approach, whereas in nanobio you use a top-down approach when you have something big and then you strip it down until you get a small stuff and use that small stuff for the benefit of biotechnology. And now let us try to appreciate the nano itself, the dimension at nanoscale. The scale of nano is a billions of meter, and nanofield typically involve a manipulation of material that have a scale between 1 to 100 nanometer or maybe 200, 300 nanometer like that. Hydrogen atom have the size of 0.1 nanometer. Water molecule is around 0.3 nanometer. The width of DNA double helix is around 2 nanometer. The virus is typically between 20 to 400 nanometer. The wavelength of the light, which we know that composed of different color, can be anywhere between 400 to 800 nanometer. If you see here, the virus is smaller than light. Hence, that's the reason why we cannot use light. We cannot use a normal microscope to see the virus. We need to use a special microscope. We can make sense of millimeter or centimeter because we can have a ruler and see it. But for nanoscale, we know it's billions of meter, but how our mind can make sense of that? How small is small? To give you an idea how small is nano, this is my actual hair. And I put my hair inside a microscope, and this is not a normal light microscope because, as we said before, in order to go into nano, you cannot use a light because the resolution of light microscope cannot be smaller than half of the wavelength of the visible light. For example, if you have an object that is 200 nanometer in size, you cannot see it using light because half of the light wavelength is around 200, which is the limit of the resolution itself. However, if you use electron wave, you can resolve this 200 nanometer object. An electron will generate a corresponding wavelength depending on its applied voltage. Typically, the generated wavelength is much tinier than the wavelength of the light. For example, at 5 kilovolt, an electron will generate a wave around 0.0173 nanometer, which is more than enough to resolve 200 nanometer object. Typically, in electron microscope, you will see black and white image. And this is not black and white as in color. It's more like a contrast. Because a color is just a reflection of light. Without light, you cannot see a color. This both is red because the red wavelength in a visible spectrum is reflected to my eyes. However, if it is dark, you cannot really see the red color. Here, you can see a little bit because there are light from the computer. If it is completely dark, you cannot really see anything. Okay, back to my hair. The magnification here is around 70-ish. Now, I magnify further 10 times from the previous image. Using the scale bar provided, you will see the size of my hair is around 127 micrometer. Bear in mind that 1 micrometer is 1000 nanometers, and surely this 100 plus micrometer is far away from nano region that we defined before, which is typically below 100 nanometer. Now we magnify it further, so this picture depicts my hair that is 2000 times bigger than my actual hair. Here you can clearly see the scales of the hair. Let us focus on one scales there, and then we magnify it further, and this image is 10,000 times magnification of my original hair. If you look at the scale bar down there, you will see it's 2 micrometer. And 2 micrometer is typically the size of normal bacteria. And if we try to fill in the area of the scale, we found that it will be around 100 plus bacteria. Remember again, 1 micrometer is 1000 nanometer. So the bacteria size is far from the nano region. And this is the image of real bacteria on a nanofiber matrix. And this bacteria is around 2 micrometer in length. And as for the fabric itself, even though it's made from a nanofiber, the fiber itself is not really clear from here. You really need to magnify it further to clearly see the fiber itself. Okay, let's say we take this area. The image here is 50,000K. Try to magnify it 4 times more, meaning that 4 times 50, which is 200,000 magnification, we got this image. So only at this point, at this magnification, you can see the fiber clearly. If you look at the scale bar here, is 200 nanometer. And if we try to compare with the diameter of the fiber itself, we can see that the fiber is around 10 to 20 nanometer. To give you the idea about the smallness of the scale, this is the image of the bacteria that we see before. And to put this into perspective, one scale in my hair, you can put around 100 plus of this bacteria. And that's only one scale. And compare it with the diameter, the width of the hair, not the length, the width of the hair, because we focus on the width, not the length, the width of the hair, which is itself is very small, less than a millimeter. As you can see, nano is just making things smaller, a lot smaller. For an atom or a cell in your body or a bacteria even, being small is just the way they are. But what is the benefit of you deliberately turn something that is original big, like this cube, into this cube, a smaller version of it, or even going further down into a nanoscale, making a nanocube? One benefit of making things smaller is that you increase its available surface area to its own volume, meaning that the surface area to volume is higher for a smaller object and lower for a bigger object. Before we try to understand surface area to volume ratio itself, we need to first ask for what reason we need the high surface area in the first place. Let's say you have a cup of tea and you want to sweeten it with 5 grams of sugar. You can either use a cube of sugar or you can use a granulated sugar, a table sugar, normal table sugar. Depending on your choice, it will affect on how fast you can serve your tea. Both sugar have the same chemical composition, in the same sugar, and the same volume, 5 grams. The only thing that affects its dissolution rate in your tea is its physical size. Typical table sugar dissolves much faster than a sugar cube. So getting things smaller cause the reaction occur faster. In case of your tea, it's sweetened faster. But why? It's all because the surface area. More surface area means more contact with the solution. More contact means more reaction occur at the same time, hence a faster rate. Let's say this cube represent our sugar cube. If we cut it into half, we basically generate a new surface shown in yellow there. Further cut reveal more surface. So for every cut, you end up with more cubes. And with that, you got more new surface. Let's say each side of our sugar cube is 1 centimeter in length, around this size. This face will possess an area of 1 centimeter cube. This is the total surface area of this cube. After we halve this cube from all sides, we will obtain 8 equivalent cubes. When we halve from each side, the length becomes 0.5 cm, giving each face area of 0.25 cm cube. Multiply by 6, we got 1.5 cm cube. And because the total number of cube is 8, the total surface area will be 12 cm cube. And this value is double than our original cube area. If we repeat the same process for each cube here, you will get another 8 cube. The length now becomes 0.25 cm, giving each face an area of 0.0625 cm cube. Multiply by 6, we got 0.375 cm cube for each cube. And here we don't just multiply by 8 because the 8 is just coming from this portion only. When you take into account all the portion, the number of cube will be 64. And this 64, you time it with the surface area for one individual cube. So you get 24 centimeter cube. And this value is double than previous. By repeating the process by halving each of the individual cube, and you get another 8 even smaller cube where each side is 0.125 centimeter. So here you get another 8 from this portion. Take into account all the portion, you will get total number of cubes now is 512. You can use the same calculation before in order to find the total surface area for individual cube and also total surface area for all the cubes here. Once you got the idea, you can simply tabulate in Excel in order to speed up the calculation. In real life, that's how you do it. When things shows a pattern or you know the algorithm, you can always use Excel to ease your calculation. That will save you a lot of time compared when you need to manually calculate like we did before. So we start with one cube having an individual cube length of 1 centimeter here. As we see before, the first cut will give you 8 cubes, then 64 cubes, then 512 cube. So the total number of cube here is basically 8 to the power of the iteration itself, and you get 8, and then you just drag it down so you get what you want. And for individual cube lengths, we know that after each cut the length will be half. So after this we got 0.5, and 0.5 is basically this one divided by 2. So you got 0.5, and then you can drag it down, is your calculation. Surface area for individual cube will be this individual cube length multiply with itself and then multiply with 6. So you get 6 there, and then you drag it down. Total surface area of all cubes, this individual cube surface area multiply with the total number of cube. So it just simply 6 times whatever here. So you get that, and then you can drag it down. It's important to note that when things get smaller, their individual surface area decrease. If you have this one cube shrink to this cube, of course it possesses a smaller surface area. But if by going smaller means that you have to chop this big cube into many versions of smaller cubes, then the cumulative surface area of that smaller cubes will be far higher than the surface area of the original cube. For a bigger cube like this, I can simply hold it with my hand. But if I cut this cube so that individual cube will be this big, I will got this much of cube, 512 of that. I cannot even hold everything in one hand, showing that the total surface area increase when you make things smaller. Sugar cube typically in millimeter scale, while table sugar is typically in millimeter scale. So how much chopping you have to do in order for your cube to be in nano size? Pause this video and try it yourself. And centimeter is hundreds of meter. To get to nanocube, each length must be in nano length. Nano is billions of meter. From centimeter to nanometer, you have to go smaller 10 millions time. In other words, after scaling down 10 millions time, you will reach 10 to the power of negative 9 meter. But here the column is in centimeter. So in order to know what value in this row that we need to reach in order to get to nanocube, we have to correlate our target scale 10 to the power of negative 9 or nano region to our original scale, which is centimeter. So when we do the calculation, we will see that the nano is also equivalent to 10 to the power of negative 7 centimeter, meaning that once the value of the cube reaching this level, it will be in nano length. So in Excel, you just drag down this cut iteration. Let's say maybe we go until 21, and then we see the individual lengths because we aim for 10 to the power of negative 7 centimeter here. So we drag down until we see the first instant of 10 to the power of negative 7. So here you can see that you need 20 successive cut in order to get into Nanocube. That with Excel. What if you are in exam hall and you got only your calculator? It is still simple to calculate so long that you know what you are aiming for. Here you are aiming for 10 to the power of negative 7. So what you do is that you take 1 centimeter, divide by 2, you get 0.5. Divide again the answer by 2, you get 0.25. And by doing that, the calculator already store the information, the formula for you. So this is 2 iteration. You do again, you get 0.125. That is third iteration. Fourth iteration give you 0.0625. Fifth, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And you see now, the value is already 10 to the power of negative 7 there. So here you know, you need 20 iteration in order to get to nanometer. And that's how you do it. And if you look here, if you drag down the number of cube, you get around more than million, more than billion cube there. And that billions cube make a total surface area of about 6 million centimeter cube. Typical area for the football field is 100 meter by 70 meters. Do your calculation and you found that your nanocube total surface area is enough to cover 9 football field. And that is a big surface area to cover coming from this small cube. As we said, more surface area means more area of contact with surrounding, leading to more reaction to occur simultaneously, leading to faster reaction. An increase of surface area here is a result of the addition of surface area of many cubes. But what about individual cube itself? What if the cube is alone now? We know that making an individual cube smaller reduces its surface area. Let's now throw volume in the story. For a cube like this, a calculation of volume is simply a multiplication of width, height, and depth. Similar to surface area, when you go down like this, you also reduce the volume. So both surface area and volume reduce when you go smaller. So does it mean there are no benefit of making it smaller individually in the first place? Not necessarily, because if we divide surface area to the volume here, we will observe an increasing trend. As things get smaller, its surface area to volume ratio increase. Likewise, as things get bigger, its surface area to volume decrease. Okay, calculation is one thing. You can see it from the calculation. But in real life, what is the implication of those? To understand, we need to remember that volume and surface area coexist together. An object with volume like this cube also comes with its own surface area. When you change the object volume, you also directly change its surface area. However, the rate of change is not equal. Increasing the object volume twice of its original size does not make its surface area also increase by twice. Let's take our cube again, but this time we make it bigger. 1 centimeter length will give 1 centimeter squared face area and 1 centimeter cube of volume. 2 centimeter length will give 2 centimeter squared face area and 8 centimeter cube of volume. 3 centimeter length will give 9 centimeter squared face area and 27 centimeter cube volume. 4 centimeter length will give 16 centimeter squared face area and 64 centimeter cube volume. And finally, 5 centimeter length will give 25 centimeter squared face area and 125 centimeter cube of volume. Okay, you might ask, for surface area, why I am using only one face? Why not using all the face? The relationship will be still the same. Try it yourself. Because we are just interested in pattern rather than the exact value, it doesn't really matter whether you use an area of one face or the entire area. If you look carefully, if you try to find a pattern, the correlation between surface area and the volume as cube become bigger is not linear. From one cube to another cube, a surface area increased by factor of 2 or square, while the volume increased by the factor of 3 or cube. So what is the implication of this mismatch? Volume usually correlate with weight, while surface area typically correlate with rate of reaction, or in case of cross-sectional area, it correlates to strength. It is easier to break these toothpick than to break this big wood, even though both are made from the same wood material. If you break the toothpick, it has a smaller surface area here compared to this wood which has a larger surface area here. But this wood, even though it's hard to break, it is much heavier than the toothpick. From the relationship that we just learned, if we double the cross-sectional area of this toothpick, it will become twice stronger but 3 times more heavier. Even this cube here, if you model it with steel, small cube will weigh about 8 gram. But double its size, suddenly it become 63 gram. Triple its size, it become 200 gram. Quadruple it, it weighs around 500 gram. Going one step further, it will be almost 1 kilogram. So you see here, by scaling up the size just by 5 times, the cube already beyond 100 times heavier than the original. If you compare the surface area, not the one in the red circle here because this includes all the surface area of the smaller cube, but rather you compare the one in the green circle here, you will see an increasing pattern, but it will not be as faster increase as the weight. If you apply the surface area by 6 to take into account all the surface area available on the cube, the pattern will be still the same. The reason for this is very simple. Take this 4x4 cube. It was made from 64 small cube. Total mass include all cubes masses, including the one deep in the center. But for the surface, those deep in the center cube did not add up to any surface calculation. We find in nature that large animals have disproportionately thick legs compared to those of small animal. The bigger the animal, the faster they are getting heavier than their strength can sustain. Elephant, rhinoceros got thick legs while deer, antelopes got skinny legs. This guy does not need thick legs as water buoyancy already provides necessary support. Understanding the relationship between surface area and the volume will let you to easily dismiss the following clip as a fiction. Okay, King Kong may exist, but for it to be fast and agile, it just doesn't match, as its strength will not be able to cope with its own weight. Okay, now let's talk about surface area as an indicator of reactivity. More surface area meaning more place for reaction to occur. Reaction can be anything: explosion, diffusion, rate of solubilization, etc. Let's say we make an agar from this cube. Then we soak it in a glass of water with a purple dye. After a few minutes, we take all the agar out. If you cut each agar cube in half, you will see this. As cube become bigger, yes, its surface area increase, which give more space for a dye to diffuse into. But it is not fast enough to keep up with the cube increasing volume. Hence, the dye is not able to fully occupy the entire volume. At microscopic level, living cell must contend with the fact that the growth of volume is faster than the growth of surface area. Cell like this agar cube obtain their food by diffusion through their surface. As cell grows, their surface area increase, but not fast enough to keep up with their increasing volume. For example, if the surface area increased by 4, the corresponding volume increased by 8. 8 times as much mass must be sustained by only 4 times as much food. At certain size, the surface area of the cell isn't large enough to allow sufficient nutrient to pass into the cell, which places a limit on how large cell can grow. So, cell divides. My hand, your hand, is made up by not a single cell, but a collection of a billion of cells that continue to divide since your birth. So, when you eat to get bigger and taller, you are not really increase the size of your cell, but you just increase the number of your available cells. So, there you go. Surface area and volume, they exist together, but when change comes, either by getting bigger or smaller, they will behave differently. And because of this different surface area to volume ratio exists to compare effect when things get either bigger or smaller. If surface area and volume rate of change are equal, then there are no need to find any ratio in the first place. We see before our sugar cube become nanocube, But you don't need Nanocube in order to enjoy your tea. Normal table sugar size is more than enough to get the job done. If we want to see the real effect of nanoscale in real life, just look at Gecko. When this gecko or lizard are on the wall, there are attraction force between the gecko feet and the wall. Attraction between objects can happen in many ways. Gravity attraction or pull can occur when an object has very big mass, like the gravity of our sun keeping our Earth on its orbit through space-time warping. Attraction can also happen if there is magnetism, static electricity, or simply use of sticky adhesive, or in this case glue. But this gecko do not use any grip of claw like this koala climbing a tree, or extrude any wet sticky glue like this nail attached to the wall. Their feet here is just dry, and if you look under the naked eye, it's just simply a smooth surface. When scientists study gecko, they found the secret. Microscopy has shown that the gecko foot, or we call it pad, has nearly 500,000 keratinous hair, or we call it setae. Each of setae itself is very small, and at the end of that small setae, there are another projection of spatula branch structure. We call it spatulae. When you see closely at this foot, you will see this are made of from hundreds of hair. We call it setae. And each of these setae is around 100 or even less micrometer long. The diameter of my hair that you see early in this video, the diameter itself is alone bigger than this setae length. And the width of this setae is 1/10 of the hair itself. At the end of the setae, there are still another projection of even smaller branch. We call it spatulae. They can be up to 1,000 spatulae per each setae end. And each of these spatulae is 200 to 500 nanometer in size, which is itself in nano region. And the structure name comes from its shape, which looks like a spatula. And this tiny branch of spatulae make an intimate contact with the wall. And when things get intimate, weak intermolecular attraction force like van der Waals can start to show its effect. What is this van der Waals force? If you have two neutral stuff like this near each other, they don't really attract, as they don't have any polarity difference. But everything, including this boat, is made of an atom, and in an atom you got an electron buzzing around a nucleus. Sometimes the electron is here or here or here, so the electron cloud in an atom is keep moving. The positive charge of the nucleus and the negative charge of the electron keep everything in neutral state. When there are two neutral objects near each other, this electron moving can cause a partial polarization. In an atom, electron is like a probability cloud. If, for instance, an atom A have its electron move to the right like here, and for an electron B, also most of the electron move to the right like here, the distribution of electron will be like this. And because the distance between these two atoms is intimate, the negative electron cloud in atom A will be distorted toward the positively charged nucleus in B, and this will cause a temporary and instantaneous attraction between these two atoms. And because the electron will keep moving, changing in direction here and there in the orbit of an atom, the attraction will be only temporary and also instantaneous. And this attraction force, we call it van der Waals, will weaken rapidly over a distance. But if the distance between objects is very close and intimate, as in case of gecko feet on the wall, van der Waals force can predominate. The attraction itself is very weak individually, but collectively, it can contribute to significant attraction force. In gecko, we see before that each feet have 1,000 of small setae. And when every single individual setae in gecko feet intimately touch wall surface, cumulative van der Waals attraction force is sufficient to hold the entire gecko mass. The intimacy of gecko feet with the wall comes from its spatulae nano size. Because it's very small in scale, it can fill up every nook and cranny exists on the wall, making a near perfect contact. Our hand here cannot do that because our palm is just simply one surface without tiny hairy setae like a gecko. Even if I have this glass slide and I press my finger on it, there are not much van der Waals effect happen. If we zoom in this glass slide, we will see the flat surface here is not really flat, similar to our fingers. Most of it consists heel and valley, and because our finger doesn't have small spatulae like Gecko, it cannot fill in that valley. And as we said before, van der Waals force weaken over distance, and because of gap between this valley, the attraction force caused by van der Waals force is not significant at all. So does that mean if we have gecko-like hairy setae on our hand, does it mean we can move on the wall like a gecko? In other words, is this clip real?
Our safety systems are working.
The safety systems are completely failing.
We're very safe in here.
The occupants are...
Spiderman is just a fiction. Remember, surface and volume exist together. Even if this Spiderman have gecko-like feet hairy structure, and can utilize van der Waals attraction force to the fullest by creating a perfect contact of all available surface, his own body weight will be against him. Remember, the bigger you become, the faster you get heavier than your surface area can expand. The only way you can cling to the wall is by using very stickier glue, adhesive or vacuum, meaning that you don't rely on the van der Waals force alone. But then, now, you just stuck on the wall. As to move forward, you need to unstuck yourself from that stickier glue first. Gecko is different. You see the lizard in your home, they not only can attach to the wall, they can only move or unstuck itself very easily and doing it very fast. Get attached to the wall is one thing. Get detached from the wall is another thing. To move, you need to have both. Scientists found that gecko is about the largest size something can become to walk on the wall before weights become a problem. As animals increase in size, the amount of body surface area per volume decrease. An ant has a lot of surface area and very little volume, and an elephant is mostly volume with not much surface area. This poses a problem for a larger climbing animal because when they get bigger and heavier, they need more sticking power, but they have comparatively less body surface available for sticky footpad. This implies that they are maximum size for animal climbing with sticky footpad, and that turned out to be the size of gecko. And because gecko walk on the wall not because of the sticky adhesive but rather due to the van der Waals effects, studying gecko really embodies the effect of nanoscale and surface area to the volume. Many researchers has tried to mimic gecko adhesive mechanism. For example, this guy from Stanford University in the next clip used gecko-inspired pad to climb the wall. Wait, did I say before that it is not possible for human to be gecko even with perfect van der Waals effect as their weight will act against that? If you read their work, they mentioned they are inspired by gecko, but they never said that they use 100% gecko mechanism. This is stress sensor image of one gecko feet on a flat surface. Blue color is for adhesion while the red yellowish color is for compression. Only a fraction of adhesive area on a gecko feet produce large adhesive stress, indication that load sharing in gecko feet toe is not ideal, which is logical in itself. If gecko have to use 100% of their feet area in order to attach using van der Waals effect, then the moment gecko want to move, he will fall down, as raising the feet to move surely will disrupt that van der Waals attraction. The researcher did mention in their paper about this problem. So they solved the problem by using the concept called digressive load sharing concept. If you're interested to know further, you can read their work. Nowadays, you can even buy a gecko-inspired adhesive, better known as mechanical adhesive, in the market. This is an example of how fundamental research at nanoscale in the lab can be realized into making a real product. So, when you go nano, your surface area increase, and we have seen many benefits of having high surface area. The benefit does not stop there. When light is shown to a smaller stuff that have specific geometric configuration, it can result to unique optical effect. Take for instance this iridescent color of this butterfly wing. You see blue, right? This pen is also blue, but they are different between them. My pen is blue because of there is blue pigment in it, but for this butterfly wing, there are no blue pigment at all. So where the blue color come from? Similar to rainbow formation, there are no blue pigment out there to start with. This butterfly iridescent blue color is a result of light interference. Microscopic scales of butterfly wing and tiny water droplet in atmosphere provide microscopic structure that allow light to refract, to reflect, to disperse and interfere at different wavelengths, causing coloration to happen. This type of color is called structural color, a color caused not by chemical pigmentation but because of physical structure. Talking about color, do you know that when you have a gold and you make it smaller and smaller, the color will not be gold anymore? At 100 nanometer, gold nanoparticle is purple in color. Going smaller at 20 nanometer, the gold nanoparticle is red in color. Here, the effect is caused by something called surface plasmon resonance, the dancing of gold surface electron when it receives energy from visible light. But point to ponder here. How do you think people made gold nanoparticle? Do they really cut a block of gold into a smaller size? And if it's true, what machine they use? And what is the benefit of having gold nanoparticle to Bionanotechnology? That is your homework to find it out. There are many more stuff happening at nanoscale. Graphene, a flat layer of 1 atom thick, is known for its electron mobility, making it suitable material for the development of quantum computer. Carbon nanotube, due to its strength, could make space elevator possible. Quantum dot, a kind of nanoscale semiconductor, can itself emit a pure color of red, green and blue light, which improve the vividness of our TV display. Cellulose make this paper, and this paper come from the tree. But when you turn it into nanocellulose, you get a stable colloidization as gravity does not bother them anymore. And you can use this nanocellulose as food thickener. Biological entity like phospholipid can reorganize and reassemble together spontaneously by itself due to the difference in hydrophilicity and hydrophobicity made up our cell membrane. And the list of benefits that come from the nanoscale goes on. Now we have done with definition and appreciation part. Let's go to the scale. Because nano is not a scale that we are commonly see in our daily life, scientists often have to relate nano with something common that can be compared with in order for them to communicate with those who are not coming from a scientific background. When nano engineers create a nanomaterial using a top-down approach, they are typically start with a material from macro scale. And knowing how to do unit conversion between different scales is a very important skill that allows them to come out with a correct end product. Instead of using many zeros to display very large or very small number, the use of prefix before unit will simplify the matter. Each prefix here is a metric prefix and can be used with any units except angstrom. It is a special unit used only for a length unit because the diameter of atom is on the order of 1 angstrom. Diameter of hydrogen atom is about 1 angstrom. Angstrom is typically used when referring to an atomic radius or size of the molecules and spacing. 1 angstrom is 10 to the power of negative 10 meter or 0.1 nanometer. Here is just to give you an idea how big the scale is. If you count 1, 2, 3, 4 non-stop by allocating 1 second per number up until 1 billion, you have to spend 32 years in order to finish the counting. You have to remember all this prefix and its corresponding symbol by heart for your calculation purpose. We see before nanometer as a measure of length of our nanocube. But nano doesn't revolve around length alone. Meter is just one of the 7 SI base unit. Other SI base unit include mass, which is in kilogram, time, which is in second, concentration, which is in mole, temperature in Kelvin, current in ampere, and lastly the luminosity, which is in candela. From these 7 SI base unit, you can derive many other SI unit. For example, SI unit for volume is meter cube, which is equivalent to a volume of a water that can be contained in 1 meter by 1 meter by 1 meter container. But it is very big volume towards width, hence people invent liter. 1 meter cube is equivalent to 1000 liter. If you want to know how big a cube container in centimeter dimension that can hold 1 liter water, first you convert 1000 liter to 1 liter, then to meter cube, then to centimeter cube. 1 liter is equivalent to 10 to the power of negative 3 meter cube, and 10 to the power of negative 3 meter cube is equivalent to 1000 centimeter cube. For a cube, each side is of equal length, and by taking a cube root, a container will possess a dimension of 10 cm by 10 cm by 10 cm in order to contain 1 liter of water. Nanoscientists often use liter as their reference unit of choice when they are in laboratory. If a volume smaller, they just add a prefix like a micro, a nano, or a pico in front of the liter. Pressure is simply force over area. Newton is SI unit of force which derived from SI base unit that made up mass, length, and time, while square meter is a SI unit for an area, which derive from the SI base unit of length. Pascal, on the other hand, is SI unit for pressure itself. 1 Pascal is 1 Newton over meter square area, equivalent to a pressure felt by a square meter of paper when an apple rests on it. Nanoscientists often use this Pascal unit when they want to compare the strengths of nanomaterial, adhesion or compression force, etc. In Bionano, calculation mostly involve a base unit of length, mass, time, and concentration, which is the amount of the substance. We already familiar with the first 3 in our everyday life, but mole need a special mention as it is indeed specifically dedicated to a small stuff. What is mole? It's simply an amount, a big amount. 1 dozen of apple equivalent to 12 apple. 1 mole of apple will be equivalent to 6.022 times 10 to the power of 23 apples. The number itself is known as Avogadro numbers. That is a lot of apple. If we view 1 apple as a sphere with a radius of 5 cm, when we calculate, we got a volume of 5.2 times 10 to the power of negative 4 meter cube. If you time that with the Avogadro number, you will get around 3 times to 10 to the power of 20 meter cube in terms of volume. Our moon is 2 times 10 to the power of 10 kilometer cube in volume, which is equivalent to 2 times 10 to the power of 19 meter cube. Compare these two numbers together, it means that if you can clump 1 mole of apple together, its size will be bigger than our entire moon. So you can see there are no practical value of mole here. But if we talk about small stuff like a water molecule, then we can see the practicality of our mole. Our periodic table already provide a molar mass for each element. As our water molecule made up of 2 hydrogen and 1 oxygen atom, its molar mass will be 18 gram or 18 gram per mole. In other words, if this water is 18 gram, it will contain 6.022 times 10 to the power of 23 water molecules in it. With that in mind, how many water molecules in this beaker? In order to play with mole, we need mass. But here we only have a volume. From volume to mass, you need a density. Density is mass over volume. Because water density is 1 gram per centimeter cube, when you calculate 500 milliliter will equivalent to 500 gram. 500 gram water will be equivalent to 27.7 mole, which give you 2.8 times 10 to the power of 24 water molecules. Understanding how to perform conversion with mole is important in Bionano. For example, when you're dealing with glucose biosensor, the reading from the sensor can be either in milligram per deciliter or millimole per liter. These two units are not equal. Molecular weight of glucose is 180 gram per mole. Hence, 1 millimole per liter will be equivalent to 18 milligram per deciliter. For practice of converting between scales, take your phone and convert it in length to micron, its width to angstrom, and its thickness to nanometer. Here is the sample solution for width only. 1 cm width will be equivalent to 1.5 times 10 to the power of 7 nanometer. It is easy when you see the solution in front of you like now. But believe me, many students get it wrong and struggle before to solve this very question. I believe it is important for me to go a little bit tangent here. I suggest you pause and reflect a code in front of you now, which may give some hint why sometimes you found yourself struggle during exam. Let's do some exercise here. Pause this video and try to solve the problem first and then compare your answer afterwards. So this question is about proportion or scaling. We did scaling up using a cube before. We also learned about unit conversion, prefix and sphere formula. Necessary dimension is also given to you in this question. So you should be able to solve this question. If you are yet to do it, I suggest you pause first and try, because once you see the answer, the effect of learning diminishes greatly. Come on, pause it and try to solve it first. My phase diameter here is about 9 cm and the diameter of hydrogen atom is 1 angstrom. When you do the calculation, my phase is about 900 million times bigger than hydrogen atom, but that is only for the diameter. How big here means the volume. If you divide the volume of the phase and the volume of hydrogen atom, you will get 7.29 times 10 to the power of 26, and this is the amount of hydrogen atom that you need to have in order to fill up my entire phase. The second question asks you where is the outermost electron if your phase now become the nucleus of the hydrogen atom. We know for an atom, the nucleus resides at the center while the electron orbiting this center. The size of hydrogen atom will be proportionally increased as the size of the nucleus increase. So this is simply a problem of ratio. The ratio here is between the radius of the nucleus and the radius of an atom. If you divide the radius of the nucleus and the radius of an atom, you get the value of 62,500. Hence, when the nucleus radius magnified to 4.5 cm to match my phase radius, the radius of the hydrogen atom overall also magnifies by the amount of 62,500 times. Hence, when the nucleus of the hydrogen atom is this big, the outer boundary of this hydrogen atom can be found at the distance 2.8 km from here, and that's where you can find the outermost electron. Now let us talk about magnification and demagnification. It is not the same thing as scaling up or scaling down. When you scaling up something, you physically make it bigger, but when you magnify something, you only just optically make it bigger. This boat seems big under magnifying glass, but if you remove the glass, its original size still maintained. During magnification, having a scale bar is important. We have seen this bar before. Let's put everything in practice. You have an image A and image B now. Scale bar on A is 20 nanometer. Scale bar on B is 2 micrometer. If image A shows this boat, what happened to this boat when you go to B? The image will be demagnified 100 times. Pause this video and try to make sense of it, as the correlation between the scale bar and magnification times is important to understand when dealing with a small object. Let's do another practice. Image A here shows a nanofiber on a copper grid visualized under a scanning electron microscope. How big is this copper grid in real life? It is this big. On this grid, there are many holes and each hole is 40 micrometer by 40 micrometer. Your task now is to find what is the scale bar of image A and image B, and finally estimate the fiber thickness in angstrom. Again, pause this video and try it yourself. And this is how you find the answer. Tackling this question covers scales conversion, unit conversion, magnification, scale bar, and estimation in one go. This is a gelatin fiber produced from electrospinning, which is used to reinforce an alginate. An alginate is a substance that is usually used as a raw ingredient to make the agar. The reinforced hydrogel here will be then used as a corneal transplant. This is the paper that discussed that experiment. From this paper, try to work out how much improvement in percent experienced by the alginate hydrogel when the aligned gelatin fiber was added to it. So simply pinpoint the original value, the reinforced value, and then do the necessary scale conversion and find its percentage increase. So here you can see by reinforcing the gel, the alginate gel using the aligned gelatin fiber, you increase its strength more than 1000%. But to get this value, initially you need to convert the kilopascal to megapascal and then find the percentage. So that is why scale conversion is important. With that, we basically conclude this video, which is about Bionano, its definition, appreciation of nano, and scale conversion. On that note, thank you for watching.